Up to this point, we've been able to use the same 4 basic rules for integration, but now there's a situation where the rules of integration that we have don't always apply. Today, we look at the idea of integration by substitution, where we take a given function and make it fit the rules that we already know. You can see that these rules are identical to the ones we already listed, with the exception of now we're dealing with u as opposed to x as we were before. And what you're going to find is these u's are going to be functions with respect to x. And then du is going to be the derivative of that function. For example, if we look at the integral of x squared plus 4 to the 6th power dx, what we want to do is we want to choose a u value from this integral. Typically, the function of highest power is what we're going to choose for u. So we will choose u to be x squared plus 4. Before looking then at the integral, we want to find the derivative of u, or du. Using our rules of integration, we get that du is 2x dx. You'll notice now that we have u to the 6th power, and then this creates du. We can rewrite our integral now to be u to the 6th du, which applies to the rules that we already know. Our integral becomes u to the 7th over 7 plus c, and then we substitute back in the value that we chose for u, getting x squared plus 4 to the 7th over 7 plus c. Likewise, on this next example, we're going to follow the same process. We want to choose a u value. Typically, again, we want to look for the highest power, so we are going to choose u to be t squared plus 1, and then taking the derivative of u, we get 2t dt. We now have du and u on the bottom. This integral can be rewritten as 1 over u du. From our rules of integration, we know that 1 over u is the ln of the absolute value of u plus c. And then we simply substitute back in the ln of t squared plus 1 plus c. The same process applies here, and you notice there's not a second function. Let's then take this to be our u value, 5x plus 1, and so du is simply 5 dx. We have then the integral of the square root of u, but we don't have du. We're missing a 5. We can simply multiply by 5 and then divide out front by 5, or multiply by 1/5, leaving us with 1/5 square root of u du. Using our same rules of integration, we can rewrite this as u to the 1/2, which gives us 1/5 u to the 3/2 over 3/2 when we add 1 plus c. And then simplifying our fractions, we get 2 over 15 u to the 3/2 plus c, or 2 over 15 5x plus 1 to the 3/2 plus c. Remember, you can multiply by a constant to get the du that you need, but you also have to divide by that same constant. Here, anytime you have something e to a power, that's going to typically be your u function. U is going to become x squared plus 3, giving us a du of 2x. We're missing the 2, so I'm going to multiply by 2, which means I have to multiply by 1/2 out front. Notice the 7 can then come out front, and so I'm left with 7/2 integral of e to the u du. We know our rules for integration is going to give us 7/2 e to the u plus c, and then we simply plug back in our value for u, giving us e to the x squared plus 3 plus c. In this example, you might not be sure what to choose, but remember, pick the value of highest power to be your u. This gives us a du then of 3x squared. We're missing a 3, so we multiply by 3 and bring a 1/3 out front, which gives us 1/3 the integral of du over u to the 5th. It may be helpful to rewrite this as 1/3 u to the -5 du, which gives us 1/3 u to the -4th over -4 plus c. And when we simplify that, we get -1/12 u, over u to the 4th plus c. And substituting back in, we get -1/12. Our u was x cubed minus 1. So we have x cubed minus 1 to the 4th power plus c. Just my 4 there. As a last example, let's consider a square root, but also a value up front. Again, take the piece that has the higher power, x cubed plus 1, which leaves us with du of 3x squared. We have then what we need, and so we can then simply adjust this to having the integral of u to the 1/2 du. We raise this and we end up with u to the 3/2 over 3/2 plus c. Flip that fraction and we end up with 2/3 u to the 3/2 plus c. Substituting back in our u value, we get 2/3 x cubed plus 1 to the 3/2 plus c.